We have 3 papers. First one is efficient rendering for light field displays using tailored perspective mappings. Then we'll have efficient spatial resampling using PDF similarity. And lastly, we'll have the barycentric quad rasterization. So the first paper is efficient rendering for light field displays using tailored perspective mappings. And the authors are Laura Fink, Svenja Strobel, Linus Franke, and Mark Stamminger. And I think Svenja will present.
Okay, I hope you can hear me. So first of all, hi. Have you ever experienced annoying rendering lags, for example, when playing a game or when working with 3D models in a software like Blender? Well, I've surely experienced that a lot. And believe me, it will probably be worse if you're working on light field displays. So hello, my name is Svenja Strobel. I'm a student at the Friedrich Alexander University of Erlangen-Nuremberg. And in the next 20 minutes, I'm going to introduce you to our paper, teach you something about parallax-based light field displays, why the traditional rendering method for these is rather inefficient, and how we can make it better by using tailored projective mappings. But before I dive into explaining our algorithm, first of all, some basics on these displays. Oh. Yeah, some basics on these displays. So first of all, what are light field displays? Light field displays are basically displays that create a 3-dimensional effect without the need of special 3D glasses like those you would need for VR or something like that. Here on the slide, you can see the example of the looking glass portrait display, which is the light field display that we use to implement and analyze our algorithm. Parallax-based light field displays usually work in a rather similar fashion. They kind of display different images in different directions. That means that if you look at the display from like the left side, you just see a different image than if you're looking at from the right side. This then also means that each of your individual eyes sees a different image. And this then leads to stereo vision and parallax, which creates this 3-dimensional effect in your head. If you want to render 3D scenes for these kinds of displays, you can't just do this in the traditional way because you need these multiple images to be able to filter them out later on. In order to do this, we first of all render the scene multiple times with these slightly offset skewed frustra, and then end up with multiple rendered views. From all of these rendered views, we then combine them into one single image, which we call the interlaced image, by subsequently taking individual image strips from each views and placing them next to each other. So you start off and kind of take a strip from view 0, then from 1, 2, 3, then you start off and take an image strip from view 0 again, 1, 2, 3, and so on until you filled this entire interlaced image. This image then contains about equal amounts of all views, and is then the image you actually see on the display itself. These parallax-based light field displays usually display this interlaced image behind some kind of optics, for example, lens arrays or barrier masks. Here in this macroscopic demo I created in Blender, you can kind of see how these optical systems then filter out the individual views depending on your view angle at the display. In order for this to work really well, the interlaced image has to match the display optics in front of it perfectly. And in order for this to work, there are some important terms regarding this interlaced image. First of all, there's the so-called tilt, which simply describes this rotation of the strips in the interlaced image. This tilt is usually applied to reduce moire artifacts. Then there's also the so-called pitch, which describes the amount of repetitions of all views in the interlaced image. In our example here, the pitch is 2.5 because we're repeating views 0 through 3 around 2.5 times in this image. In reality, these pitches are a lot larger. For example, our pitch for the looking glass portrait was around 250. This then leads to these individual strips becoming very thin, thinner than a pixel in fact, and just everything becoming very small. This then also leads to the necessity of a so-called subpixel offset, which is necessary to match the offset of the LCD crystals on of the display in the interlaced image itself. This offset is usually just an index shift for the red, green, and blue channels, and just means that we have if for the red channel, we start off with index 0 in the bottom left corner. For the green channel, we, for example, start off with index 1 in the bottom left corner of the image. And for the blue channel, we start off with index 2 in the bottom left corner. The subpixel offset is important for later. So why do we even want to do efficient rendering for these light field displays? Well, you may already suspect that this traditional algorithm is not particularly efficient. We're rendering all of these different views, but then only combining them into this one single interlaced image, which is what you see on the display itself. In a naive calculation for the looking glass portrait, we're only using around 27% of rendered pixels in this interlaced image and throwing away around 72% of pixels. This is not really great. What you would want to do instead is to only render the parts of the individual views that actually end up being used for this interlaced image and are displayed on the display itself. And this is what we propose to do in our paper. And our idea is rather simple, in fact. So what we want to do is, first of all, to change the rendered area of our individual views to this rotated bounding box you can see here in blue. We just simply want to match the pitch of these strips to align our pixel grid with the rotation. Then, now that we have an aligned pixel grid, we can simply adjust the width to skip the unused areas and end up with this kind of squished individual views. For the new width, we can use the pitch because the pitch, on the one hand, describes how often all views are repeated in the interlaced image, but this inversely also means that the pitch means how often each individual view is used in the interlaced image. So by simply setting the width to this pitch, we then skip exactly the areas we don't want to render and end up rendering the strips we want. From these squished, condensed views, we can then reconstruct the interlaced image by simply applying the inverse mapping in the interlacing shader. And it should be noted that for our approach, we ignore the subpixel offset and simply align our indexes with the green subpixel channel. So here, once again, what we do is we adapt our thruster to this rotated bounding box of the original scene and then adjust the width to be the pitch. We then render the views, and while rendering, we also apply a mask to skip the shading computations for the areas which will not be used during reconstruction. Then in the interlacing shader, we apply the inverse mapping to reconstruct the interlaced image, and with a more realistic pitch, it looks more something like this. And then, as before, we can simply display it on the display and end up with a nice three-dimensional looking scene. So much for the idea. Now, does this work? Or does it not work really well? In order to test this, we used 3 different scenes of varying complexity. We had the simple teapot scene, the Buddha scene, and the complex coconut scene. We also varied our render configurations. For the resolution of the individual views, we had 3 different configurations. The low resolution configuration correlated with the real-time recommendation from the manufacturer. The medium resolution configuration correlates with the offline rendering recommendation from the manufacturer. And for the high resolution configuration, we just try to push it as much as possible by using the native display resolution for each individual view. And then we also varied the number of views between 48 and 108 views. Then we ran multiple experiments on these test configurations, first of all looking into the memory requirements of our results compared to the traditional rendering method. In all of these evaluation slides, our results will be displayed in red, and the ground truth is displayed in blue colors. So here for the memory requirements, you can first of all see that our approach renders significantly less pixels than a traditional method because our width is now fixed to the pitch, and we only increase the number of rendered pixels linearly with the number of views and the height, while of course the traditional rendering method scales quadratically. Then this memory reduction also led to a render time reduction. We can see here that we have significantly faster render times for scenes with many views and high resolutions. But we also see that we reduce the render time in all configurations, even if not that much. For the more complex coconut scene, we see that we do not have such a great speed up as here, where we especially say, like in the teapot scene, we save especially a lot of time during the interlacing phase, so we have a lot of reading operations on the image containing all of our rendered views. And this is rather slow in the reference result because it's just a huge image. And due to us reducing the number of rendered pixels, it just becomes significantly faster here. In a scene with more, where the rendering actually takes up more time, we don't have such a great speed up as with these simple scenes where the rendering is already pretty fast, but we can also speed up the render time, cut the render time in half for the highest configuration of the coconut scene. So great, we reduced the memory and the render time. Now, does this negatively impact our results? In order to analyze this, we did a quantitative and a qualitative evaluation. First of all, here you can see the quantitative evaluation, where we are looking at the root mean square error of the configurations against the reference high resolution configuration. For the simple teapot scene, which doesn't have a lot of texture detail, we see, first of all, that the error is very small, ranging only about 0.3%, and that it decreases in a similar fashion as the ground truth when increasing the resolution of our configurations. For the more complex coconut scene, which has many high resolution texture details and many high frequency changes, we see that our error is quite a lot higher, ranging around 3.4%, and that unfortunately, when increasing the resolution, we do not decrease the error as much as the reference algorithm. So we now see we have errors in our images. Now, where did these errors appear? Here you can see the absolute pixel difference of one configuration of the Buddha scene, and we can see here that the error is especially located around high frequency areas, so around the edges and in high contrast areas. Here for the teapot scene, you can see especially well how this error actually looks like. We see that it appears as these sort of staircase artifacts resulting from us rotating the frustum and also ignoring the subpixel offset. By doing this, we introduce the systematic error. So now this is what the error looks like in the interlaced image, but the interlaced image is of course not what is perceived directly on the display. So do we see the error on the display? Well, the answer is at least for the small looking glass portrait display, we were not actually really visible to see these artifacts on the display itself due to the resolution of the individual views rendered out in each direction being rather low resolution, and the display also having a rather high built-in depth of field effect. For other displays, of course, this error may be visible, and that's why we also asked ourselves if we can further reduce the error and by doing super sampling, if the error was visible on the display for a larger display. And the answer is yes, we can do this. We also can apply fine-grained super sampling in our approach. So first of all, here you can see our current situation where we ignore the subpixel offset. We reconstruct our final color by only taking the colors from the green subpixel strips. What we would want to do instead is, of course, also kind of render the red and blue subpixel strips. And we can do this because the subpixel strips are only offset by this slight index shift. So we can align our frustum with the red, green, and blue subpixel strips simply by jittering our projection matrix a bit. A naive algorithm with which you could implement this is, first of all, kind of align your frustum with the red subpixel strips, render 48 views, then you jitter it a bit, align it with the green subpixel strips, render 48 views again, then you jitter it and align it with the blue subpixel strips and render it 48 views again. And then you could reconstruct the final color from the accurate subpixel strips. Of course, this algorithm where we render 48 views 3 times is not really efficient at all, but the similar effect could probably be achieved by using temporal methods. So now for a quick summary of what I've talked about to remind you of the big picture. What we do in our papers, we use tailored projective mappings. We rotate our frustum to align the pixel grid with the tilt of the individual strips, reduce the width to the pitch, and then reconstruct the interlaced image by applying the inverse mapping. By doing this, we can reduce the memory time and the render time. Our algorithm is also a really easy extension to this traditional algorithm in rasterization because it doesn't really change the algorithm much. All that has to be done is we need some pre-computations for certain parameters. We have to change the calculation of the projection matrix, and we have to apply the inverse mapping in the interlacing shader. All in all, this can be done in a few lines of code. We also have rather small artifacts, which can further be reduced by applying the super sampling. But of course, our approach is not without its drawbacks. It's first of all very dependent on the pitch. The pitch becomes the new width of the strips. This, on the one hand, means the pitch has to be high enough, for the individual strips to become thinner or equal to a pixel, because otherwise just skipping the unused areas by adjusting the width doesn't work anymore. And if the pitch is too large, we may not end up gaining the performance gains we want to have. We also saw that we really only have a notable speed up with large image configurations, simply because we have a large overhead simply by, first of all, rendering 48 views or 108 views. What we would want to look at more in the future is we would want to look into how well we can do super sampling with temporal methods and how we can find the best balance between performance and quality. We would also want to look into more elaborative qualitative evaluation techniques for our approach, because we found it rather difficult when constructing our paper to really qualitatively evaluate the results, because the interlaced image is not what you see directly on the display. And with that, I'm already at the end of my presentation. Thank you very much for your attention. Code is available for our approach in the traditional method through this QR code, and you don't need a light field display to run the code. And now I'm looking forward to your questions.
Thank you very much for your presentation. Like, if anyone has any questions, they can come on with the mic.
Hi, thanks for the presentation. Can you talk a little bit more about what you think is the current bottleneck of because you showed that for the smaller scenes, it was a lot very fast. And then when you went to lots of triangles, it started being slow. Can you just give more detail on that? What do you think is currently the problem with that?
So what we found was that simply for the scenes where the render time is already pretty significant, we do have a large bottleneck already by simply starting the GL pipeline for 48 views, because we have to start it 48 times. And then even though we reduce the number of pixels by quite a bit, it doesn't really scale the way we would want it to do, because we have the entire pipeline before the pixel shader and stuff like that. And for the more simple scenes where the rendering goes pretty fast because we don't have a lot of polygons, the interlacing phase where we have these reading operations on the images containing the individual views takes up a significant amount of time when rendering. And here our algorithm works rather well, because by reducing the memory, we kind of can really get rid of this bottleneck here. And it scales especially well if we have these really high resolution images before.
Okay, thank you. So as I understand, you're using a traditional rendering algorithm. Will it be possible to render such image in one pass if you use, let's say, ray tracing and for, exact projection for each pixel? Or it will produce some unexpected artifacts?
So is your question how it would work with ray tracing, or if we can simply?
Yeah, I mean,
Okay.
can such interlaced image could be rendered in one pass with ray tracing?
I think it would be possible. We didn't test it, but I thought this would also be an interesting topic for future work to extend the algorithm and implement it in ray tracing and see how well this could work. And I think it could actually perform better in ray tracing than in rasterization, because we would kind of get rid of a lot of the overhead by just starting for the GL pipeline for 48 times.
Anyone else?
I have a question regarding the spatial aliasing, like anti-aliasing. What did you do anything for that? Because if there are like sharp edges, since you have reduced the dimension in the horizontal direction, there would be like more jagged edges in one direction than the other.
Mm-hmm.
So have you applied any anti-aliasing technique in that to answer those artifacts?
So you're asking how we can get rid of jagged artifacts in sharp edges, yes?
Right, because you reduce the horizontal dimension, so it will be adding more of the anti-aliasing in the horizontal direction.
Exactly. So that's what our super sampling approach is for. I didn't show any visual results of that, but this achieves exactly this effect of kind of blurring these jagged edges a bit by interpolating between either taking the correct images from the views, or you can also just read from all three and then kind of interpolate them to kind of blur the jagged artifacts a bit.
Okay, let's thank the speaker one more time. And next we have the Barycentric quad rasterization from Jules Blumenthal.
So let's, I'm Jules Blumenthal. My talk is about barycentric quad rasterization, but it is all based upon the work done in 2004 by Professors Horman and Turini. And, but first I wanted to say, I've got some notes. I'm a little befuddled because we had so many technical issues right at the start here, but I wanted to say it's nice to be back here. I did attend I3D when it was held at Snowbird. And you can check to find out how long ago that was, but it was a great conference then. And so it's nice to be back. We've had a lot of changes since this conference was at Snowbird. And in particular, we've had the development of the GPU and shader architecture. And so that has enabled a lot of things. In particular, it has finally provided a practical implementation for the proposal that these gentlemen made back in 2004. And so, so I'm not claiming any real originality here other than to say that I realized or recognized that the geometry shader could be used to implement their suggestions. Of course, the geometry shader didn't really come around until 2010, I think, 2012. So a little after their paper. Right, the developments have been, we now have GPUs, we have shader architecture. It means we have a tremendous improvement in speed and computation power and flexibility in our programming. And the result, of course, is everything's faster and it allows us to make much more complex images, which is fantastic. But it also allows us to improve the quality of our images, which was their concern. So I want to talk about that a little bit. Their concern dates back, the issues that they're concerned with, that I'm concerned with, date back to the late 1970s. People have been trying to deal with this issue for quite a while. And it's basically, the issue is, we all know OpenGL and DirectX and all other implementations always take a polygon and break it up into triangles and render the triangles separately. And that has problems. And this is what they were addressing. So let me go on and just talk about what those problems are. So I'm going to actually try to do a live demo here. Oh, I've got to move the Zoom window up. Okay. So if I can just remember how to begin here. Here we go. So here's the problem. On the left, we have a quadrilateral. It's just a square. And you can see where the diagonal shows where it's broken into two triangles. On the right, we have the texture source. So on the right, it's just a square image with some vertical lines, and they're texture mapped onto this. And if you look at the rendering here, there's really no artifact. There's nothing to complain about. But you have to kind of understand that there can be a problem the moment we sort of break a rule of affinity. And by that, I mean, if we just consider the lower left-hand triangle here for a moment, there's 3 points, right? Those 3 points, the left-hand corner and the upper left, they correspond to these. We know that from any 3 points to any other 3 points, there is a affine transformation that will transform all 3 points from geometry space into texture space. It's an affine transformation. It's why whenever you render a triangle, it always looks good. The reason this looks good is because the fourth, when we add a fourth point, the upper right corner, and And because both shapes here are rectangles, what that means is that the same affine transformation that is applied to this triangle is applied to this triangle. The affine transformation is the same for both. However, if we move one of these vertices, we're going to break that affine similarity, and that's where the problem occurs. So just watch as I'm just going to grab the upper right-hand corner, and I'm going to start to move it. And so you can see along the diagonal, all of a sudden, you know, here we have bars going up vertically, but now they're at a tilt. Rather bad continuity gradient of the texture here, because the transformation that that's applying is not the same as this triangle, and that is why we see this discontinuity. Now, we can compensate for that. I can go over here, and I hope you can see this little magenta point here. It's basically saying this is where the upper right-hand corner should be. If I move it to where it says it should be, then all of a sudden we see that the discontinuity goes away. And so that's nice. However, we are not free to go around moving texture coordinates. I mean, it would be nice if we were, but it would change the appearance of things. So how to show you that, how to prove that? Let me go back to the slides I have here, and let's just take a look at the sphere. You know, probably the simplest shape we can imagine, right? If we are talking about a standard Mercator projection, where we're texture mapping a Mercator map onto the sphere, then here is, if we're dealing with a Mercator projection, it's typically parameterized according to longitude and latitude. And so naturally the sphere creates quadrilateral. So here we have constant latitude above, constant latitude below, and then constant longitude to the right and the left. That's how spheres tend to be parameterized. And what you can see, what's readily should be apparent, I'm sorry the image was cut off here, but that's the equation. Quadrilaterals are pretty square, but as you move towards the pole, the quadrilaterals become trapezoidal, and then have a generous upper edge. So quadrilateral, in effect, is a triangle at the pole. And so the shape of these quadrilaterals are changing as we move to the pole, but the parameter doesn't change. So inherently, we are going to have a problem maintaining any sort of affine transformation. And so that implies that there is going to be, or can be, serious discontinuities when we texture map a sphere. I hope this is a surprise to some of you, because it was a surprise to me when I noticed it a few years ago. I actually thought that I had been confused, and that somehow I had been texture mapping properly, but all of a sudden things weren't working. But in fact, when I investigated, I realized, wait, this is a problem that just has been existed for decades. So let me just go on and talk about the solution that Horman and Turini proposed. I want to make sure I'm not getting out of order. Yeah, so they proposed this solution, which is to say that every pixel, if at a given pixel, we can know the attributes of the corners of the quadrilateral. So they might be texture coordinates, they could be color, they could be surface normals. But that at a pixel within the quadrilateral, we want to have some sort of weighted averaging of the four corners of the quadrilateral, their attributes. And the solution that Horman and Turini came up with is to determine the weights based upon the angles formed at the pixel and, going around and two of the corners of the quadrilateral. So, so in fact, you can compute the weight of the vertex on. So it just mathematically all worked out very nicely. And Horman and Turini were careful to point out that this works. It gives a continuous solution even for quadrilaterals that are severely twisted, not necessarily planar. And it also works for quadrilaterals that span the image plane. So if you have points behind the eye and some points in front of the eye, that can cause serious trouble for certain methods, but it does not cause a problem for this particular method that Horman and Turini proposed. So, so let's take a look at really what happens here. So I'm going to go and show a sphere, and I'm going to turn off. There we go. So on the left is what you get if you just texture map a sphere with that pattern I showed, and you let OpenGL do what it normally does: divide each quadrilateral into triangles, render the triangles separately. You get severe, I think they're pretty severe artifacts. It's not just that there's a discontinuity in the gradient of the texture, but and the paper goes into this in a little more detail. But in fact, when we get to the pole and that quadrilateral has become a triangle, that triangle represents only half of the quadrilateral. It represents only half of the texture space. So we're not only getting discontinuities here, we're actually getting texture that's actually being completely ignored. And so, so if you were landing at the North Pole of some planet and you had a Mercator projection, you were looking at it, you would see something like this if you just render as OpenGL would have you, or if you invoke Horman and Turini's algorithm, you get something on the right, which is, I think, a lot better looking. What's interesting here is that if I turn off the texture, so I've turned off the texture, and let me kind of zoom out a little bit. Notice without the texture, we don't see any of those nasty discontinuities. I mean, it kind of looks fine. Why is that? Well, it's because as we go to the pole of a sphere, guess what? The normals all start converging. So let me just, again, just to be clear, I turn on just to show the normals here. So again, if I look, you can see at the poles, the normals are all converging to straight up. So the fact that we're on the left, we're doing triangle rendering, quad split. On the right, we're using, we're not seeing any real difference because there isn't any particular difference as you go around the top of the pole. There isn't any real difference in the normals. So with texture mapping a sphere looks bad, and this barycentric method can correct it. But if you're not texture mapping, it doesn't really look too bad. However, I want to say when the Journal of Computer Graphics Tools published the paper, I got one response a couple of days later from an old friend of mine, Paul Haverly. I don't know if anyone knows Paul, but he's been around for many years, and he does really some very cute artistic things with computer graphics, and he's very concerned about quality. And he called me up and said, I just saw your paper, and I've been having a problem with cones. I don't know what he's using cones for, but he says, I see shading problems with cones. Might your method here correct that? And so I just wanted to show what happens when we look at a cone, because at the tip of a cone, we don't have a convergence of surface normals as we do with the sphere. So here's a cone. And so again, at the very tip, you can see the surface normals continue. They're basically parallel with the normals at the bottom. So there is no convergence of the normals at the tip. And I hope you can see, I know the lighting's a little light. There are definite discontinuities that you can see. Barycentric method, the discontinuities disappear. And so really that's, the main thing I want to present is that, for some of us, this cone is perfectly fine, but for some people, they're not happy with that, and the cone on the right would be much better. So really that's the gist of the paper. And so I just kind of want to conclude with a couple thoughts. It's kind of a plea to all of you and to the graphics world and in general. And that is that we need the quad. The quad is very, very useful for ruled objects, ruled surfaces or developable surfaces. A quad is a very natural basic element. And if you were to look at industrial design, if you were to look at the community of people that do meshing, you'll find that their elements are triangles and quadrilaterals. And by extension, they'll talk about tetrahedron and hexahedron, but hexahedron being basically a quad, being a cube, basically. So the quad really is a fundamental modeling primitive, and we really should not ignore it. It's very valuable. And so it is distressing, I think, that OpenGL has deprecated the quad. They deprecated it years ago, but it's still there if you kind of know how to make OpenGL recognize it. I guess you have to use the core OpenGL. But, I occasionally see on the net, comments by people saying, hey, the quad is broken into triangles anyway, so we really don't need the quad. Let's just get rid of it. I think that would be a huge mistake. And the other plea I want to make is that I hear from some of the GPU manufacturers, I won't mention any NVIDIA names or anything, but I do hear suggestions that, let's get rid of the geometry shader because, the geometry shader does present something of a hiccup in the vast stream of vertex data coming out of the GPU and sent to the vertex shader. The geometry shader kind of causes a little discombobulation there. Well, okay, you don't have to use a geometry shader. You don't have to build it into your shader program if you don't want to. But it is a little distressing to hear some of the manufacturers talk about, let's just get rid of the geometry shader. That would be, I think, a huge error. The geometry shader is so valuable, I think, especially for issues about quality. And in particular, in case you're wondering, it's how we marshal the data of the four corners of the quadrilateral. The geometry shader takes in those four corners and then kind of sends it on to the pixel shader so that when the pixel shader is called, you know where the pixel is, but you also know what the attributes are for the four corners. And so you can perform this barycentric interpolation. If we got rid of the geometry shader, we would not be able to do that. So, I hope everyone will write their boss immediately and say, please send a letter to whoever and tell them we need the geometry shader, we need quadrilaterals. They really are useful. I think that's all I have to say.
Let's thank the speaker. Thanks very much for a great presentation. Does anyone have any questions?
Yeah, I have a question about your last point, and it's a little bit of philosophical kind of question, because recently we've seen with some developers actually saying that hey, we don't need any rasterization at all. Like there was fantastic talks from Epic Games about technology called Nanite, where they use, for small triangles, they use it all just in software, in compute shaders. They rasterize them in software. And given like this trend among developers who want more control, want less things in hardware, but instead do some things more efficiently in fully programmable shaders, like compute shaders, what would be your argument to those developers that why would we need a quad primitive, especially in hardware, if you can emulate a lot of it in software?
Oh, that's a good question. I haven't thought about that. I mean, it's a good question. I think something tells me that no matter what is possible in software, hardware rasterization is always going to be faster. I could be wrong, but I mean, from the from the late 1970s or even earlier than that, hardware rasterizers are, as highly optimized, and it's but we'll see. That might be possible. I think if you're talking about other alternatives like ray tracing, yeah, you don't need to worry about this. But on the other hand, it's hard again to imagine ray tracing ever competing speed-wise with rasterizers. But Turner Whitted, the father of ray tracing, a great guy, used to be out here, used to be at Microsoft for a few years, then went to NVIDIA. And I think he's no longer with NVIDIA, I think, but he said, hey, our goal is to have high-speed ray tracers. So I don't know what the future will bring, but all I know is that I looked at a sphere a couple of years ago and said, this doesn't look right. And now I look at it and say, it looks right now. So I'm pleased we have this capability, but the future keeps changing. So thank you for that question. And any other questions?
We have one more.
Apologies that I haven't read the paper yet, so I'm not sure exactly how you pass the data through. But when you're talking about needing the geometry shader to do this, is it just about being able to export multiple like triangles from your input? I'm wondering if the need there is satisfied by mesh shaders, because I think that in people proposing to get rid of geometry shaders, there'll still be mesh shaders now going forward that give you some of that control, and I'm wondering if that's enough to achieve the same result.
It sounds like it is. I'm not too familiar with mesh shaders, but assuming the mesh contains quadrilaterals, and it presumably would provide the same information that I'm presently using the geometry shader for. So yeah, like I said, things change a lot, but right now the geometry shader is very valuable.
Thanks for the talk. I love the geometry shader as well. I teach about it to my students. In practice, here, do you? Sorry, I haven't read the paper, but in practice here on this cone example, it's modeled with, you're assuming that at the point you have a quad, right?
Yes.
And then what is the geometry shader in practice doing? Are you remapping the UVs or are you outputting a quadrilateral?
No, not remapping.
Okay.
Simply, the geometry shader takes in four corners and allows you then to output what you would normally output to the pixel shader. In other words, the vertex that's really being processed. But then the pixel shader says, oh, I got a pixel, but I also have the information for the four corners. I know what the attributes of the four corners are, and also I know the location of the four corners, so I can.
The agency, you use that.
Right.
Yeah. Thank you.
Couldn't you hack this? Couldn't you hack this? I'm starting to think about doing this without a geometry shader. And what if you just like went disgusting and duplicated your vertex positions and you set it in as like an extra vertex data stream? Then you would be able to do this in a vertex shader by just always including the missing vertex, essentially the adjacent vertex or the opposite vertex of every single vertex in the quad. And then you could still feed that into the pixel shader and get appropriate barycentric interpolation for quads.
That might be another way to do it. That could work. You know, the code is in the paper. So if that's one of the nice things about that journal, you know, they really want you to include code. So you can just look at the input to the pixel shader and just see this is what it needs. And so if there's a different way to do it than the geometry shader, that's fine. But you can see what the pixel shader needs. What's that? But you know, every year we have more and more memory to spare. So
one more.
So how does this compare in performance to the traditional triangle barycentric? Is it a couple more divisions per pixel or something?
You mean how does it compare to normal triangle rasterization?
Yeah, the calculation that you showed.
I did kind of calculate. There are about 100 arithmetic operations in the pixel shader to compute to deal with this barycentric method. So, you know, one of the suggestions in the paper is 100 arithmetic operations. That's kind of a heavy lift for a pixel shader, maybe. So one thing, you know, might be you can look at your attributes and your quadrilaterals to begin with, and you can decide, you know, some of these quadrilaterals might not have this affinity issue. They might be perfectly good. And so you can just render them per normal using splitting the quad into two triangles and not worry about it. And so it's a little extra overhead, but it might speed things up a fair bit. I haven't tried that though.
Okay, thanks.
Let's thank the speaker one more time. And our last paper in this session is Efficient Spatial Resampling Using the PDF Similarity by Yusuke Tokuyoshi.
Hello, my name is Yusuke Tokuyoshi from AMD. Today, I'd like to talk about efficient spatial resampling using the PDF Similarity. This is a technique to improve Listia. Spatio-temporal resampling Listia is a powerful technique to increase the number of candidate samples for resampled importance sampling. It reuses samples from past frames and spatially neighboring pixels. However, reusing spatially neighboring samples is not always efficient for highly detailed scenes because each pixel has different target PDF due to geometry edges, normal maps, spatially varying materials, and shadow edges. When the target PDF for the reused pixel is significantly different from the integrand at the current pixel, the reuse can increase variance. This mismatch also increases bias for biased Listia variants that reuse shadow ray visibilities. For example, Listia with visibility reuse using two shadow rays per pixel produced darkening bias around the shadow edges. For aggressive visibility reuse using less than two rays per pixel, it lost shadow edges. Therefore, we reject samples that have dissimilar PDFs. In previous work, Listia rejected samples from reuse using some heuristics, such as the similarity of geometries. This approach uses the depth and normal at each pixel. Lin et al. Used roughness parameter and edge length for their connectivity of passes. However, these heuristics didn't support shadow edges and arbitrary material. In this paper, we introduce a new method of rejecting spatial reuse based on the similarity of PDF shapes. Since the target PDF includes the shadow term and BSDF term, our method can reduce variance and bias around shadow edges and material boundaries. By using our method for a Listia variant that uses shadow ray visibility, we can reduce the number of shadow rays while preserving shadow edges. Our contributions are as follows. We introduce a rejection heuristic based on the similarity of PDF shapes for Listia. To perform our method at real-time frame rates, we approximate the PDF shape using a von Mises-Fisher distribution for single bounce path connections such as direct illumination. We also present a temporal estimation for this VMF approximation. To handle the temporal estimation error for animated scenes, we use a hybrid method that combines an existing rejection heuristic and our PDF similarity. Finally, we demonstrate the effectiveness of our method for several Listia variants with different visibility computation methods. Okay, let me show you a video for our method. For 2 rays per pixel, the previous rejection heuristic introduces a darkening bias in shadows. Using our method, we can alleviate this darkening bias. Okay, let me show you the difference by toggling our method and the previous method. Okay, next, I'd like to show the case for 1 ray per pixel. For this aggressive visibility reuse, the previous method loses hard contact shadows. Using our method, we can render hard contact shadows without tracing 2 rays per pixel. Okay, next, I'd like to explain our rejection heuristic. In the Listia algorithm, a target distribution is given, but it is not normalized. For our method, we use normalized target PDFs instead of the unnormalized target distributions to compare the shapes of distributions. However, it is computationally expensive to obtain this normalized target PDF. We cannot compute the normalization factor analytically in most cases. Furthermore, it is infeasible to compare the exact PDF shapes between pixels. Therefore, we roughly approximate the target PDF to achieve real-time frame rates. For a single bounce path connections, the PDF can be expressed with a spherical PDF at the shading point. We approximate this spherical PDF with a von Mises-Fisher distribution, which is a normalized spherical Gaussian. This VMF distribution is an isotropic single lobe distribution represented with axis and sharpness parameters. This is a visualization of VMF lobes with different sharpness parameters. The sharpness parameter corresponds to the reciprocal of variance of Gaussian distribution. And this is VMF lobes with different axis parameters. The axis parameter corresponds to the mean position of the Gaussian distribution, but it is restricted on a unit sphere. By approximating the spherical PDF into this simple lobe representation, we can compute the PDF similarity inexpensively. For this VMF approximation, the VMF axis and sharpness parameters are obtained from the average direction of the PDF. This average direction is given by the integral of the product of direction and PDF. Therefore, we estimate the average direction by sampling light directions every frame. This is a linear algorithm with our rejection heuristic. The left side is the same as the existing linear algorithm, except for the spatial rejection heuristic. For our heuristic, we add the right side average direction estimation. This average direction estimation is a biased variant of linear. Unlike the regular linear, our average direction estimation performs temporal resampling only and doesn't perform spatial resampling to preserve shadow edges and material boundaries. To reduce the number of shadow rays for our average direction estimation, we reuse the visibility over time similar to existing biased linear methods. In addition, we reuse the initial sample from the lighting estimation. Therefore, our average direction estimation does not trace additional shadow rays, while it can introduce a small bias. Linear gives an important light direction, but one sample is insufficient to estimate the average direction. Therefore, we average the sample light directions over time using resampling weights. If the scene is not animated, this estimator is a variant of weighted importance sampling or ratio estimator. Thus, it has a bias due to normalization, but the bias reduces quickly for temporal continuities. This is a visualization of estimated average direction for each pixel. In this scene, average directions are different between shadowed and lit pixels. By using these directions, we detect shadow edges for our rejection method. Once the average direction is estimated for each pixel, we convert it to a VMF lobe. Then compute the similarity of two VMF lobes between pixels. In this paper, we use a product integral-based similarity to evaluate the overlaps of PDFs. Thanks to the VMF approximation, this product integral has a simple analytical solution. However, this approach ignores the shift of light directions between pixels. If a scene has only one point light source, the PDFs are delta functions, and there is no overlaps between pixels since we ignore the shift of the lobe axis. Therefore, to obtain the similarity based on the distance between shifted directions for such high frequency PDFs, we smooth the estimated VMF lobes. Then we compute the similarity of the smoothed VMF lobes. For the detail, please refer to our paper. This is rendered images using our rejection method and the previous rejection method for visibility reuse linear with 2 shadow rays per pixel. As you can see, our method reduces variance as well as darkening bias for contact shadows. For the visibility reuse linear, we can use a smaller number of shadow rays than 2 rays per pixel. However, it loses contact shadows for the previous rejection method. On the other hand, our method preserves contact shadows more than the previous method for a small number of shadow rays. This figure shows the case in Listia without visibility reuse. For this case, we use 5 rays per pixel for exact visibility test in our implementation. Although our rejection method introduces a small bias, it significantly reduces variance around the shadow edges and material boundaries. Next, I'd like to show the bias for converged images. Our method introduces a small bias in dark shadows. We can see this bias in the visualization of error using the symmetry mean absolute percentage error metric. However, it is barely perceptible in the rendered image. As you can see, the bias is negligibly small. Next, I'd like to talk about how to handle the estimation error of our temporal estimation for animated scenes. Since the average direction is estimated using a temporal resampling technique, our rejection heuristic can fail for animated scenes. For example, our estimation can have a significant bias and variance when the accumulated sample count is small, such as for temporal disocclusions. Furthermore, the variance of our PDF similarity can correlate to the variance of lighting, because our average direction estimation shares the initial samples with lighting estimation. This variance correlation results in a bias in the rejection of spatial reuse for the lighting estimation. Although the variance is decorrelated by using different random numbers in every resampling routine, the variance and its correlation may be noticeable when the number of temporal samples is small due to temporal disocclusions. Therefore, our method is not suitable for temporal disocclusions. In addition, the temporal average of sample directions can have temporal delay for animated scenes. Therefore, we use our rejection heuristic only when the sample count is sufficient. In this paper, we interpolate our heuristic and existing heuristics, such as geometry similarity, using the temporally accumulated sample count. Using this combination, our heuristic based on the PDF similarity is effective only for temporally continuous pixels. To reduce the delay for animated shadows, we reject rapidly moving lights from temporal reuse for the average direction estimation. This is done by reducing the accumulated sample count when a reused sample light direction changes significantly. In this paper, we use a spherical Gaussian-based reduction rate for the change of the light directions. Although this approach introduces a bias in the average direction estimation, it is not a problem, because reduction of the accumulated sample count makes existing heuristics more dominant than our heuristic. I'd like to show our experimental results. Although our heuristic helps to render high frequency shadows, unlike the previous heuristic, it works only for temporal continuities. For temporal discontinuities, our method uses the previous heuristic as a fallback. Therefore, the visibility reduced list here with 1 ray per pixel. For 1 ray per pixel, it can lose shadows in motion, as in the previous method. However, we can compensate the lost shadows by tracing more shadow rays based on the temporal continuity. This temporal continuity is given by the temporally accumulated sample count for light directions, which is used for interpolating our heuristic and previous heuristic. These images are rendered using the combination of our rejection method and adaptive shadow ray tracing for a moving camera. Although our method is not effective for temporal discontinuities as in the previous method, spatio-temporally adaptive ray tracing preserves shadows for temporal disocclusions. When camera moves, this approach traces more shadow rays than spatially adaptive ray tracing and can increase a darkening bias as in 2 rays per pixel. But it produces more highly detailed and temporally coherent shadows inexpensively. Let me show you a video for temporal disocclusions. This is a combination of our rejection heuristic and adaptive ray tracing. As you can see, it renders highly detailed and temporally coherent contact shadows while using less than 2 rays per pixel. Next is a glossy scene. The previous method ignored materials. On the other hand, our method supports glossy occlusions because our method considers the BSDF term in the PDF. It also improves glossy highlights when camera stops. Our method can be used for indirect illumination as well as direct illumination by using virtual point lights. For this thing, we can improve the quality of indirect shadows when the light source stops. Although our method is efficient, it has some limitations. Our method is a biased and inconsistent estimator due to the reuse of initial samples from lighting estimation. However, the bias is negligibly small for temporally continuous pixels, as shown in our experimental results. Our rejection heuristic works only for temporal continuities, so we use the previous method as a fallback for temporal discontinuities. To compensate lost shadows due to this fallback, we can use temporally adaptive shadow ray tracing. Our method can approximate different PDFs into an identical VMF lobes. So our rejection method can have false positives, but it's not so significant for shadow edges. Our method supports single bounce only. Extension to multi-bounce illumination, such as glossy to glossy interreflections, is left for future work. Okay, so our method, our method have a memory overfit for to estimate average direction. In our experimental implementation, the reservoir data size is 16 bytes per pixel. The reduction of this reservoir data size is also left for future work. we have presented a technique to alleviate the temporal delay for moving lights. However, our PDF similarity estimation still has a temporal delay for highly glossy surfaces viewed from a moving camera. This temporal delay results in variance for moving glossy highlights in the rendered image. For such view direction changes, we are currently considering the integration of analytic glossy lobe similarity or decoupling of incoming radiance and PSDFs into our direction estimation. We would like to investigate the efficiency of these approaches in the future. To conclude our work, we have presented a new rejection heuristic based on the similarity of PDF shapes. To perform this rejection heuristic at real-time frame rates, we introduced an efficient VMF approximation and temporal estimation for the PDF shape. We have also presented a stable combination of an existing rejection heuristic and our PDF similarity, considering the estimation error for the PDF shapes. This combination produces a comparable image quality to the existing heuristic for temporal disocclusions and rapidly moving lights. On the other hand, for temporally continuous lighting, our method improves the image quality while using a smaller number of layers than the previous method. That's all for my presentation. Thank you for your attention.
Thank you very much for a great talk. I think we're a bit late on time, but I think we have time for one question.
Thanks, it's nice work. So I wonder if you have compared with the unbiased version of Research DI, because you know that
unbiased
version, right? Because you compute the unbiased weight for samples in the unbiased version, so that should have also some effect of not having the bias, having correct shadow. So how does your method compare with a unbiased version of Research DI?
So the comparison with unbiased MIS is shown in this slide, and the difference is here. Yeah, so there is very small bias, but it is negligibly small.
I mean not the conversion image, the real-time rendering. How does the quality?
Real-time version.
Yeah, that's for example, you have only one sample pixel. So how does that look like?
Okay, so yes, experimental results is shown in the our paper. So yes, so our method, reduces variance. So even for one sample, both for one sample case and many sample cases. Yeah.
Okay, I think if you combine your method with the unbiased research, you have a better quality overall, right?
Yeah. Yes.
So that thing's always really impressive work.
Thank you.
Okay, let's thank the speaker one more time.